Thank you.
Thank you. Hello everyone, I'm Indy from UCLA. So I'm going to talk about our study on the name server selection of DNS caching resolvers. This is a collaboration of UCLA and the Verizon Labs. So according to the DNS specification, a DNS domain should be supported by at least 2 authoritative name servers. So when a caching resolver needs to query a DNS domain, it may want to select one of those authoritative name servers to send the queries. And some caching resolvers may prefer to select the fastest name server to query so that they can minimize the latency of the whole DNS lookup. While some others, they may prefer to distribute queries among all those name servers so that they can avoid overloading the fastest name server, and they can make their server selection behavior unpredictable to prevent some malicious attack. And even for those caching resolvers that prefer the fastest name server, they still need to query those unselected name server from time to time so that they can tell which one is the fastest. And in this work, we're trying to answer 3 questions. The first one is, do all those caching resolvers select the fastest name server? And if we found some caching resolvers that do not select the fastest name server, instead they choose some slower one, we want to understand if that's a mistake or they just intend to do that. And the third question is that the network is not always stable. Some name server may become unresponsive occasionally. So we want to know if the caching resolvers can detect the unresponsive name server and even can detect the recovery of those unresponsive name server. So we have tested 5 different implementations of caching resolvers, including Band, Power DNS, Mbound, DNS Cache, and Windows DNS. And for Band, we have tested 2 versions, Band 9.7 and Band 9.8. So here is an illustration of our test bed. So our measurement is a trace-driven measurement. We collect a DNS lookup trace from ISP's resolver's log. We use a trace replayer to reproduce the DNS lookups and send them to the tested caching resolvers. And all these tested caching resolvers use their default settings. Since the name server selection is only meaningful when we are talking about one domain, so we choose the .com domain in our test bed as the target domain. We set up certain name servers for the .com domain, and we put a network emulator in front of these name servers so that we can create different packet delay and packet loss. And to redirect the DNS queries to the .com servers, we also set up a root server. And since most DNS lookup cannot get the direct answers from the .com server, we also set up a name server for the second level domain. And we use the wildcard so that all those DNS lookup can be terminated at this server. And the query trace we used lasts for 10 minutes. It contains about 3.5 million DNS lookups, involves 400,000 unique DNS names belonging to 150,000 second-level domains under the .com domain. And the average iterative query rate between the caching resolver and the .com domain is about 250 queries per second. But this query rate could be higher if the caching resolver doesn't have a large cache and the domains set the TTL of the DNS records to be a small value. We created several scenarios to test different property of the caching resolvers. Here we list 3 of them for discussion. In the first scenario, we want to see if the caching resolvers can tell the difference in the round trip time of different name servers so that they can distribute queries according to that. So as you can see, the round trip time to each name server varies from 50 milliseconds to 170 milliseconds. And in the second scenario, we want to see if the caching resolver can detect the unresponsive name server and then avoid sending queries to that one. So in this scenario, the first name server is unresponsive. Well, in the third scenario, we want to see if the caching resolver can detect the recovery of those unresponsive name servers. So in this scenario, the first name server is unresponsive at the beginning, but it comes back after 5 minutes. So next, I will briefly talk about how those caching resolvers select the name server. So most caching resolvers will use the smooth round-trip time to estimate the delay to different name servers based on previous queries round-trip time. And some caching resolvers use a strategy that is to select the name server with the least estimated round-trip time. For those unselected name servers, these caching resolvers will decrease their estimated round-trip time so that at some time they become the least one, and this name server can be queried again. And in those tested caching resolvers, band 9.8 and Power DNS use such a strategy. And some other caching resolvers use another strategy, that is to select the name server based on some probability that is related to the estimated round-trip time. And in this case, even some name servers with a large round-trip time can still be selected, but with a very small probability. And in our tested caching resolvers, band 9.7 and NBOund adopts this strategy. So now let's look at our measurement result. And we did find some caching resolvers that prefer the fastest name server. So here is the measurement result in the first scenario. As you can see, the graph on the right, we list the name server along the x-axis according to their round-trip time. So the first name server has the least round-trip time, and the last one has the longest round-trip time. And the y-axis is the queries that sent to each name servers. And as you can see, the Power DNS distribute almost queries to the fastest name server. But actually, Power DNS also queries the other. But since the number is very small, so you cannot see it here. And another caching resolver, band 9.7, also sends a lot of queries to the fastest name server. But it also distributes a lot of queries to the others. This is because band 9.7 distribute the queries statistically. That is, for those caching for those name servers with the round-trip time less than 128 milliseconds, and band 9.7 will select those with the smaller round-trip time with a higher probability. And even for those name servers with the round-trip time larger than 128 milliseconds, since the band 9.7 also uses the SRCT decaying, this name server can still be selected, but after some time. And we also found some caching resolvers that do not prefer the fastest name server, like the NBOund DNS cache and the Windows DNS. But the reasons for this are different. For the DNS cache, since it doesn't measure the round-trip time of queries, so it has no idea which one is better or not. What it can do is just uniformly distribute queries to all those name servers. And for the NBOund does measure the round-trip time of each name server, but it uses that as the upper bound for its name server selection. So for NBOund, it only selects those name servers with the round-trip time less than 400 milliseconds and distribute queries uniformly to this name server. And for the Windows DNS, as we don't have its source code, so we don't know the detailed reason for that. And the most weird result we found is the query distribution of band 9.8. As you can see, band 9.8 sends most queries to the slowest name server. However, when we look into the implementation of band 9.8, we found that band9 actually adopts the most traditional server selection algorithm. That is, to select the name server with the least estimated round-trip time and use the SRTT decaying to query those unselected name server periodically. However, our measurement results suggest that this algorithm does not take effects, so we try to understand why. So here, let's look at how band9A selects the name server. The graph on right shows how the round-trip time, estimated round-trip time of a name server varies in the band9-8. Actually, it varies periodically, and a period consists of 3 phases. So in the first phase, the estimated round-trip time keeps decreasing until it becomes the least one. So after that, this name server will be selected. From that time, the server enters into another phase, that is the selected phase. And in this phase, this name server will keep being selected until its estimated round-trip time has been updated by the coming responses from that server, so that its estimated round-trip time is no longer the least one. And after that, it will enter into the third phase, that is the update phase. So in this phase, the estimated round-trip time will keep being updated by following responses, so that until there is no outstanding queries to that name server. So we can notice that in these 3 phases, only in the select phase, the server can be selected. So actually, the number of queries sent to this name server can be proportional to the ratio of the length of the selected phase and the length of the whole period. And to note that the length of the selected phase and the length of the update phase is about 1 round-trip time. So actually, it is the length of the decaying phase that can determine how many queries will be sent to the slower server. However, in the band9-8, the decaying speed is coupled with the query rate. So that means if the query rate is higher, then the SRTT will decay faster. So we will get a shorter decaying phase, and more queries will be sent to the slower server. And to verify our speculation, we redo our measurement under a lower query rate. So in this case, we reduced the query rate from 250 queries per second to 25 queries per second. So now we got lower query rate, and the estimated round-trip time decays slower, and we got a longer decaying phase, so fewer queries will be sent to the slower server. So as the result on right shows, most queries will be sent to the fastest named server. So now we need to consider the factors that cause the high iterative query rate between the caching resolver and the DNS domain. So at the caching resolver side, if the resolver does not have a large cache, or the resolver serves a lot of users, then it probably generates a lot of queries in a short time. And at the domain side, if the TTL of the DNS record is very short, or the domain is very popular, like the .com has a lot of DNS records to be queried, then this domain may trigger a lot of queries. And the problem we have discussed will become more serious if there exists some unresponsive name server. So here we show the measurement result in the second scenario. Also in this scenario, the first name server becomes unresponsive. But we can see that band still sends a lot of queries to the unresponsive name server. And the reason for this result is that it's because how band treat those unresponsive name server. And for those caching resolvers that use the SRTT decaying, they treat the unresponsive name server as a regular name server, but with a very, very large estimated round-trip time. So they expect that this name server will wait a long time to decay to be the least one so that they can be queried again. However, this assumption is not true. when the query rate is high and the decaying speed is faster. So in some, when the decaying speed is very faster, sometimes the unresponsive name server may need to wait only a few milliseconds to be selected again. And the worst thing is that once this name server, this unresponsive name server has been selected, it will keep being selected until the query's timeout timer gets expired. And usually the value of the query's timeout timer is 3 or 4 seconds. So that means a unresponsive name server only needs to wait a few milliseconds to be selected. But once it has been selected, it will keep being selected for several seconds. So that's why we can see band 98 send a lot of queries to the unresponsive name server. So now let's look at how the other caching resolvers handle those unresponsive name server. So the first one is Power DNS. As we can see, the Power DNS shift all those queries from the first name server to the second. So in this case result is because Power DNS use a very, very slow decaying speed. So the unresponsive name server needs to wait about 3 minutes to be selected again. And for the Nbound, Nbound can detect the unresponsive name server. And once a name server is detected as unresponsive, Nbound use only a few queries to probe that name server until it comes back. And for the DNS cache, since DNS cache does not measure the round trip time of the queries, so it cannot detect the unresponsive name server. And for the Windows DNS, it can detect the unresponsive name server and can avoid sending queries to it. Now for those caching resolvers that can detect the unresponsive name server, we want to see how long do they take to detect the recovery of those unresponsive name server. And for Nbound, it may take up to 15 minutes to detect that. Actually, the 15 minutes is the interval between 2 consecutive probes that will be sent to the unresponsive name server. And for Power DNS, the time is about 3 minutes, and this is the result of its slow decaying speed. And for band, actually the time depends on the query rate. So as you have seen before, if the query rate is high, a lot of queries will be sent to the unresponsive name server. So it's very easy for band to detect the server recovery. However, if the query rate is low, then the band may need a long time to select the unresponsive name server. So band may wait a long time to detect the recovery. And for Windows DNS, it may take about 1 second to discover the recovery. Now here is the conclusion. It's wrong. Okay, so based on our measurement result, we found that if we want to implement a caching resolver, a comprehensive test is needed because some simile sound algorithm may not work as expected. However, for example, the SRTT decaying cannot work as we expected. The purpose of SRTT decay is to help the caching resolver to query those unselected name server periodically. However, the result is that the SRTT decaying forces the caching resolver to query suboptimal name server for a while. And another thing is that we cannot treat the unresponsive name server as the responsive name server, but with a large estimated round trip time. Because once the unresponsive name server is selected, it will keep being selected until the timeout timer gets expired. And also, since we have noticed that the impact of those unresponsive name server is significant, so once you have discovered some unresponsive name server, you should repair it as soon as possible, even though the other name server works very well, because the unresponsive name server will still attract a lot of queries from those regular name servers. Yeah, I think that's it. Thank you. Sorry, the slides is a little different from the one I submitted, so there may be some inconsistency.
Do you have questions?
Hi, Eric Zegast, ISC. I perceived that there was some sort of surprise or puzzlement that the RTT or the server selection changed between 9.7 and 9.8. Is it still unknown as to why? Is it still unknown to you as to why that changed, or that there was a change?
Sorry, I didn't get your question.
The question is it a puzzle to you that there was a change between 9.7 and 9.8 for how the RTT handling worked?
No, that's not the change between 9.7 and 9.8. It's actually the algorithm that 9.8 used. So you cannot treat the unresponsive name server as responsive one, and also you cannot select a name server, or you cannot couple the query rate with the decaying speed. Yeah.
Well, I was watching your presentation, I just looked at the release notes, and if there's still questions, it's actually in the release notes as to the algorithm changed, and here's why. So.
I think that's not the change between that, because the change between band 9.7 and band 9.8 is that band 9.8 removes the bound that band 9.7 used to have. Mm-hmm. But that doesn't help to solve this problem, because you have seen if there are some unresponsive name server, both band 9.7 and band 9.8 will send a lot of queries to the unresponsive name server. And that's because the way band treat those unresponsive name server is not very good. We should separate the processing unresponsive name server and the responsive name server in different way.
Yeah, could I? I'm Matt Larson from Verisign and was working with Yingdi on this. I mean, Eric, we are aware that the algorithm changed from 9.7 to 9.8, and we understand that the release notes say that. But the point of Yingdi's research and what he discovered is that perhaps there's this unexpected side effect of the new algorithm. That's all we're pointing out.
All right, well, we'll look into it, I'm sure.
Sorry, I thought he was going to ask a question. Michael Sinatra, Energy Sciences Network. Just a quick comment. I actually really appreciate that this is the version of slides that went in here, because I really like that last slide on implications for operators. I think it's really useful for us to understand what happens when our authoritative name servers goes down. So, just wanted to throw that in there. I think that's pretty important to look at.
Thank you.
Well, thank you, Yingdi. That was very interesting. And it is now time for our break. And please use some time in the break to fill out the survey. And enjoy a coffee from Infoblox.